So I will read quickly. There's something that I read because I'm reading, reviewing the paper, and then this thing just comes up, and I found that actually it's quite popular. Not exactly very popular, but it seems like some classic thing. So I want to talk about something called approximate entropy. This doesn't look. So actually, this is something from a paper in 1980. By Glassfinger and Caffeine. So it is a quite well cited paper. I have like 1,000 citations. And actually it appeared in Physical PLA. And but the paper is kind of, I guess it's like it picked up rather quickly, not exactly quickly, maybe in the 90s by medical people, and they used to kind of like do classification for like EEG signal and stuff like that. 1D signals. And the idea they have there is like the original paper, the intention is they try to estimate the entropy of a 1D signal, or like a, not exactly a signal, but because they're physics people, physicists, they're talking about phase space, and like they're talking about whether something is deterministic, in the sense of deterministic is chaotic, or it's actually random, really random, or like it's actually just periodic, or like they don't call it periodic, it's like order system. So you think of like you have whatever, like for example you have a pendulum, like moving back and forth, and you look at the locations and speed and so on, you can plot it in phase space. So basically, what I mean by phase space is like you have the velocity and as axis, and also have the coordinates as axis, and then like you look at like how as time goes, like how the movement goes. So if like just a simple pendulum, it would be just like something like that. So it should be a 6-dimensional space here, but I cannot draw it. So it would be just something periodic, like you just maybe a circle all the way. But if you have chaotic behavior, it will be something like, I don't know. But it's still like, it will be kind of like, to them it's deterministic. But if you have a real random system, then you're just like, everything is just really chaos. And like, one way to characterize that among the physics community is they use the Kolmogorov entropy, and I guess like the definition is a bit different from the Kolmogorov entropy in the Kofer textbook, but basically the definition is more or less the same as the shallow entropy. So basically they define something like you have a K is the Kolmogorov entropy. I don't know how to say, I'm not sure I can spell it. I'm not sure I don't spell it correct. Let's forget it. Is as let's say, let's consider, okay, let me, before I write this, maybe I write it here, to characterize the signal first. So I look at kind of the, okay, let me write down, use a probability function to characterize the signal with a probability, joint probability, I1, I2, and up to ID here. what this joint probability describes is that basically I have in this high dimensional space, and I can define in each high dimensional space some boxes, tiny boxes, and the boxes have a size like epsilon to the f, where f is the dimension of the space, f is dimension, f dimension. And I just index these boxes into I1, I2, and so on. So these are basically indexes of the boxes. And here, this joint probability is basically the probability that the signal that can be random or not random, that x, the signal, let's just call it x, that for the first sampling time, let's say delta, that it fall into the box I1. And then for the second sampling time, x t equal to 2 tau, it fall into I2, and so on up to like this x, like t equal to d tau, fall into ID here. So is that clear with this joint probability function I was trying to describe? So basically just describe for a signal that you sample d times, and like at each of the time instance, what is that signal fall into in that f dimensional space with the resolution epsilon to the f. So for example, like let's see, if I have something like that, right? If I sample it here, like this is like at time tau, and this is time 2 tau and 3 tau and so on, right? Then if this box, like let's say this box is I1 here. Of course, like what we are describing is like you can think of it as like ensemble of signals, right? So this is only one signal, but it can have. Of course, if it's real periodic, the signal will be just always this signal. But if it's random, then you actually basically ensembles many different signals, right? You have signals like that, and then like you have. At another tau, maybe the signal is here instead of here. And then like the first one is just saying like what is the probability that like at tau, that signal will be lying inside this box I1 here. And so on. And for example, if it's deterministic, then it has to be something delta function, right? It has to be always fall into not deterministic. I mean it's order. In the sense that because they say deterministic is chaotic, then it has to be lying into this box here. Let's say if it fall here, like with probability either 1, if it's always falling to that, or like if I have some other boxes that is I1 hat here, then that probability here will be 0, something like that. Okay. So if this is clear, then basically the Kolmogorov entropy is like very much like a Shannon entropy. You just do like Pi1 up to ID, and you do a log there, I1 up to ID, and then you take the sum over I1 up to ID, take the negative sign here, and then more, and then like I'm also interested that I want D to be very long, very large, so I have lots of samples, and I want the resolution to be really small, epsilon should be close to 0, and also like I have this time, this is the spatial resolution, or like not exactly spatial, but yeah, it's kind of like spatial in this sense, and this is like the time resolution that tau is also goes to 0. So that's the Kolmogorov entropy. And it has some property here that is pretty nice. That basically the k will be equal to 0 if your stuff is like really ordered. So it's yes.
In the second term is the log of I1 to ID.
The P.
Oh yes, of course.
Yeah.
So so this is like if the system is ordered system. So and it will be infinity if the system is really random. And it will be something like between 0 and infinity if it's chaotic. Or like basically it's deterministic in the definition. So of course like the problem here is this is not useful in practice, the definition. You can hardly compute stuff like that. So what the paper, the original paper, they describe is trying to estimate something like close to this k here, and they basically like their candidate satisfies something that like call it let's call it k tutor for now. Then eventually it will be always bigger than equal to 0, and k tutor will be less than equal to k. So it's like basically a lower bound of the true Kolmogorov entropy, and k tutor goes to infinity also if the system is random, and also like k tutor won't be equal to 0 for chaotic system. So okay, it turns out the paper is it's only 3 pages. It's a pretty nice paper that is very much concise. So the idea is like pretty simple also. They basically, what they did is like, okay, I need to give a revision of the, I don't know how to pronounce it. I think it's Renmi or Renmi, I don't know. It's kind of a French guy, right? It's Renmi or like what? The Renmi entropy. That is basically, okay, it's an extension of the Shannon entropy. The definition is something like you have, instead of like p log p here, sum over this x here, x, sum over this x here, the definition is like p x to the q, let's see, sum over q minus 1, something like that, I think. Let's see. I can write it down. So, let's see. I didn't write it down. I hope I didn't make a mistake here, but but it's okay because it's really an intermediate step. So if I make a mistake, then please forgive me here. But so anyway, the only thing like I want to mention this Renyi entropy is just I don't know it's Renmi or Renmi or Renmi. So is that okay, this channel entropy turns out to be just a special case of this one. Let's call it like this R, let's say I call it HR here. HR would be a function of Q here, let's say. So, okay, I put a question mark here because the definition may not be correct. You just need to look up Wikipedia. So, or like conference textbook. So, you have, actually I think Koffer didn't mention this one. Let's see. So basically channel entropy is just a special case that this one will be just equal to when you take the limit of HRQ, that limit Q goes to positive 1. One from the left hand side. And also like if you plot this like in terms of Q as a function of Q, you see like the Renyi entropy is basically like the one here, is something like this. So it's monotonically decreasing. And so because of the definition, it's kind of easy to compute when like Q is equal to 2. And of course like this is exactly what he's trying to find as a candidate for this Kolmogorov entropy is like I'll just pick Q is equal to 2 here. So then I will just have like let me use let me put it this like that. That's what he used here in his paper. So then he has this K2 here as an approximate of the true Kolmogorov entropy, and this K2 basically this K2 is the candidate of this K tutor there, and will satisfy all these conditions here. So of course if I set Q equal to 2 here, what I have is basically just reduced to K2 is equal to this limit tau go to 0, limit epsilon go to 0, limit d goes to infinity, minus summation I1 up to ID here, P I1 up to ID. Also, I'm using this Renyi entropy instead of this Travis entropy, so I should substitute this term here. So I have 1 over Q here, 1 over Q minus 1 here is just 1 here, 1 over 1 here. So it's sum over I1 up to ID here, and P I1 up to ID here to the 2s, something like that. So now we will try to compute this instead of this.
What is the Q?
What?
Q is the Q there?
Q here?
Yeah.
Yeah, Q here is like is a parameter for the Renyi entropy. So basically, for the Renyi entropy, you have it's defined this way. Okay, of course I skip all this limit stuff here, but it's just defined this way. And it's kind of generalization of the Renyi entropy that when you Q this parameter take goes a limit to 1, of course you cannot just substitute 1 here, but if it goes limit to 1 from the left hand side, then it will be just equivalent to the Renyi entropy. And of course you can substitute other Q. But if you substitute other Q, it will be just a lower bound of the Renyi entropy. So he just used this and just consider when Q is equal to 2, so reduces the chronograph entropy to this equation here. And so let's look at some special case here. Let's say for d equal to 1 here. So I mean, of course, I should consider d goes to infinity, but let's say ignore this part here. Just let's say just say for d equal to 1. Then this term here will be just sum over I, pi squared, something like that. And in his paper, I kind of denote this as C epsilon, something like this. I should write C1 epsilon, something like this. And we can estimate this C1 epsilon in the following. You think of this is more or less asking what's the probability that you have a pair, you have your, okay, I don't think it's really very precise, but it's more or less what's the probability that something is going to appear in the I trace, right? So appear in the I trace in the sense you basically revisit that place again, right? It's you have a whatever, it's consider a particular I here. Let's say I here. That is the I there for a fixed index I. This pi squared is basically what's the probability that I hit this and hit this again, right? So therefore, roughly we can estimate this as if I look at the same realization, or if I have now, of course, okay, that definition is ensembles of signal, right? But in practice, you will just have one signal, and you want to estimate what is the chronograph entropy for that one, right? And you want to use that to estimate whatever your signal is really deterministic or really random and so on, right? So then, let's say for that signal, let's say it's x1 and x2 up to xn. That's after sampling. Let's say this is the signal I have. So I can estimate this C1 epsilon here as the probability that, or let me simply immediately write as the number of pairs of NM in same box. So in the sense how many pairs do I have? That's basically n squared pair, right? So I will just approximate this probability, not probability, but this, yeah, exactly. This sum probability has this one here. And of course, when I define same box, it's basically saying that it should be less than the epsilon there, right? So it's something like I'm saying that xm minus xm is less than epsilon there. So this is for d equal to 1, and for d equal to more than 1, it will be similar, right? I can just say, if for general d, I'll just approximate this sum over pi square here, I1 up to id, p square I1 up to id. This in his paper, in that paper again, like it's defined as CD epsilon there. It approximate as like 1 over n squared number of pairs of, now it's like number of pairs like have length d such that like such that in the same, maybe I say super box because I don't know. Yeah, anyway, the same boxes. What I mean is that basically for each of them they should be differ. Basically xn minus xm plus xn minus xn plus 1 is less than epsilon.
N is the number of all possible pairs.
N is the big N is that.
Yeah.
A big N is the signal that is we are testing. Like you have like signals of length N. So something like. So I mean this is a little bit. I don't think here is very precise at what kind of norm they should use. When they first introduce it, they say like probably use first norm, then they have another paper that using the infinity norm. Then actually for people afterward, they all use infinity norm. So so in the sense like they are just looking at like the maximum, not should be with maximum of the difference of that two segments of signals should be less than epsilon. Here, of course, I'm not writing absolute. Let me just. Oh yeah, it's okay. This I'm kind of writing the first norm here, but I mean eventually they will use infinity. So that's about it, almost.
How we can estimate the epsilon?
Oh, okay. This is like a parameter. The thing is, like they have some parameter of the. They use, and they have more. After they have some paper describe how they pick the parameter, but I won't describe it here now. Let's see. And okay. Yeah, I believe I'm missing a log here. So we should have a log here. Yeah, I think I'm missing a log here. So, okay. So then I know how to estimate this thing here. So oh okay. I also like oh, here I'm missing something here. Okay, it has some normalization factor here. So here it should normalize by, because by the scale, basically it should normalize by d tau here, and so because I have over d tau here, I have somewhere here I have like have over d tau here also. D tau here. Okay. People have to watch till the end and then go back to court. So, but okay. at least if you watch until the end, you will get something correct. So okay, this is known. We have this. I mean, I don't care too much about this kind of like scaling factor here, but I care about this d here. What you can see here, I don't know whether I can use this space here. So if I substitute this notation here, I basically have K2 is something like proportional. Maybe I just write a 1 over A. D here, A is just some kind of constant, log this CD here, and D should goes to infinity somewhere. But the main point is like, if you look at this, like what do I have? I have like exponent, CD is basically equal to exponential ADK2 or something like that, right? And then therefore, like if you look at CD plus 1, it should be equal to exponential AD plus 1 K2 here. So if I take the log again, it's kind of silly going back and forth. But if I take the log again, okay, it's totally silly. Now I see. It doesn't really need it. Okay, I have this here, and I have log CD is equal to AD K2, and log CD plus 1 equal to AD plus 1 K2. So what I have is like, I have K2, if I subtract this two things here, I have log CD plus 1 over CD is equal to AK2. When I subtract this one by this one, and then also I can have like this K2 possibilities. So that is the equation they really use to compute the approximation. So basically, they pick a d there, it's like something of parameter also, and pick an epsilon there, and then compute this CD plus 1 and CD based on these equations here, and then afterward they just count, take the log, take the fraction, take the log and normalize that. Oh yes, and that's more or less about that. Oh, okay. Maybe I write down the okay. I guess probably this is okay. I guess it's and. As I said, like this is kind of used for like EEG signal and actually any kind of 1D signal. What they use is like they again like if they have some kind of diseases, then they will think that like doctors will think that like this has a chance that the signal is more chaotic or less chaotic or something like that. That will be a good feature. So just basically, you're using it, just you take the signal, compute this thing, and then as a feature, and then you just see, take lots of samples, and then again, you just do typical machine learning stuff. But this is just a way to generate feature. It appears to be like very useful. And actually, there's some paper after this one is in 2000. What they argue, like the authors, is that like this thing is kind of like not very consistent, and also like it is always a lower bound, therefore it's a little bit biased. So they do some modification of that. They call that thing like SAP. Yeah. So this module is kind of available in a number of software. Anyway, I guess I will probably just stop here. Unless you have questions. Or like I'm not sure I should write down the procedure again, but I worry that because I copied these procedures from another paper and they use a little bit different notations. So basically they have this M here is D and S long here is R. So I probably if I write this down, I'm going to mess up some of the symbols.
Yeah, I'm not sure I get true or not. For the last equations, just you want to just find the K2 in the iterative algorithm?
No, that's no iterative here.
For the CD plus 1, and you just...
Oh, okay.
You
You basically fix the D here. You fix the D and you fix the epsilon here. So anyway, let me try to write the procedure maybe. So I just need to make sure that some D is same as equal to M and epsilon is same as R. And I will try my best to translate real time. So basically you have, so in practice like you have signals, let's say x1 and up to xn here is some kind of signals you have, like incoming signals. And then like you just take M here, okay, M is D, okay, remember this, M is equal to D, I will try to say D here. So you fix a D, fix D and fix epsilon, fix D and epsilon. So you basically like you have M samples and you just take segment of that, right? So take every segment of that. So you have like this, let me denote as a X big X1, 1D here, and up to, signal X1D is basically equal to X1, X2, up to XD here, X1D, and then I have second X2 up to XD plus 1, X2D here, and so on. I have like X up to basically XD, M minus D plus 1 up to XN, this is X, M D plus 1, D, something like that. So I generated a bunch of vectors from this signal, right? Or like you can think of segments of these signals. And then like I will just count the difference of like these signals from each other. So I pick any one of these, as I pick an XID of any one of them, and then I define something like called CID epsilon. It's just the number, or actually not exactly number, it's the normalized number of vectors that is similar to this one. So basically, it's like Okay, let me, for convenience, I put this whole set of vectors into something called QD here. And X in QD, so, and I need to make sure this X should be similar to this XID here is less than epsilon. People typically use infinity long. And this is just a number. I count the size of this set here, see how many numbers is there. And then I just normalize that. The maximum number would be just n minus 1 plus n minus d plus 1, right? If I assume that I also count myself, I also count x is equal to xid here, so I just normalize this by n minus d plus 1. So then this one will be like from 0 to 1, right? It's kind of normalized from 0 to 1, or like you can think of. And that is basically an approximation of this thing, right? But I'm only counting one ID here. But if I really want to approximate this, I should just take an average of all this, right? And therefore, I take an average of them. I define CD epsilon as like CID epsilon sum over I is equal to 1 to n minus d plus 1 over n minus d plus 1. Now this is my estimate of this here. Then I do the same thing for CD plus 1 epsilon. And actually, it appears that the convention is that like when you estimate this CD plus 1, you will not change this set QD in the sense that you also use the same normalization factor n minus d plus 1 instead of n minus d. Yeah, but I may need to double check that one. But the paper I read, actually the paper I'm reviewing, can happen to have error, of course. But like this way. So, so CD plus 1 should be, let's see. So, but anyway, let's not write this because you get the idea and it may be something wrong. And then you can similarly compute CD plus 1, and then that one, K2 will be just approximate as like log CD over CD plus 1. So basically take this A equal to minus 1.
Is CD plus 1 over CD plus 1 over CD?
Yes, but I'm saying like this A take minus 1.
Okay.
Because in fact like CD will be always bigger than CD plus 1. Because you extend a little bit, it's like you have fewer number of segments will be like similar to your original segment, because now you need to compare one more component. Yeah, and that's it, and that is your estimate. Yeah, and I'm quite sure probably people have library installed that, implement this already. So, even though like if you try to implement it, just a couple of lines of MATLAB code. Yeah, try to ask all the questions and we can all take also. remember that. I don't need to.
Oh, the two K2 is different.
Say that again.
K2 the expression of two, but different. A is -1. A is equal to -1.
Yeah. A is -1 here.
-1.
Yeah, A is second -1.
Why you choose -1?
Oh, well, okay. Here I'm. Okay. Or like at the beginning, you guys should just put A here, then you guys will be happy. Or like A should. Yeah. Or like A should put -A here instead. Like we will be happy. Because like what we are doing here is basically this is always bigger than this actually. And we are really doing ourselves a favor to get a really something is defined, and then like of course you can put any kind of like scaling factor here, but rather than putting any scaling factor here, we just put nothing there. Yeah. What I mean is like probably I shouldn't really define this way. Let's see how. Yeah, if I put minus sign like here, then like everyone will be happy, I guess. Or I can do it yeah, actually that is better. Then A should be positive here.
The signal should have the special condition. We're just using this method on it or no?
No, it doesn't need any special conditions. It can be any kind of 1D, one-dimensional signal. What you're trying to estimate is just like how is that the signal is kind of real random, or like it's kind of chaotic, or like it's basically like periodic. So if it's like very much periodic, then it will be something like this estimate will be close to 0. If it's kind of chaotic, it will be something like from 0 to infinity. And if it's like really random, then it goes to infinity, something like that.
It's just used for the 1D signal?
Yeah, it's only for 1D.
And we cannot use it?
No.
We use the last version to estimate the K2. That expression to estimate the K2. But the first is also can estimate the K2. Is for
Yeah, you can. I mean, you can, but the problem is that you want to put it to infinity.
infinity.
Yeah, you want to say. Therefore, like they don't compute it. Like of course, in practice, they don't set B to infinity. They 20 something or something.
But use infinity can use L'Hopital principle to go with the first L'Hopital.
That doesn't help. I mean, your CD is kind of analytic. Your CD is something like this thing. How do you know? You cannot take derivative of
infinity
CD, right?
over infinity.
No, I mean, how do you take derivative of CD?
Explain again how to order the x1 to xd. We have a signal from x1 to xn, and we order.
Oh, okay. We just pick the first. This is h2 here.
Yeah, it's something we
So
select
just
some
no
signal and
no selection. No, there's no selection here. For example, if like I have let me erase it. Let's say x1. Let's say x is just equal to 1, 2, 3, 4, 5. Let's calculate that. 6, 7, 8, 9. And then like your t, let's say, is equal to 3. Then your first x1 d will be just 1, 2, 3. So you pick this. And then your x2 d is just 2, 3, 4. So it's and so on.
and move it and
Just.
compare each block.
And then you compare the basically each with the other. So in this case, it is not.
Yeah. And for example, for the CD and CD plus 1, we have only one term extra.
Yeah, CD to C plus 1, you will consider D equal to 3 and then you consider D equal to 4, let's say. But this thing is supposed to be analyzed signal that this n go to infinity and also D goes to infinity. Yeah. But of course in practice, it will not like, yeah. Anyway, I forward the paper to you. I mean, like, if you receive my email, that you,
Yeah.
yeah, that's the paper.
Yeah.